In this video, we will explain the convolution operation. Convolution is a powerful concept that forms the basis of many linear filters. A convolution operation involves three parts. First, we have the input matrix, and we have a convolution kernel, and finally, we have the output matrix. We convolve the input matrix with the convolution kernel to obtain the output matrix. And let's see how it is done. Imagine placing the kernel on the top left corner of the input matrix wherever it fits. And now we are multiplying corresponding elements of the overlapping regions. So we are multiplying 7 times 1 plus 2 times 0 minus 1 times 3 plus 4 times 1 and so on and so forth. So you multiply corresponding elements and add them all together to obtain the result. And that is the result that we want to put in the output matrix. Now you will notice that the size of the output matrix is slightly smaller than the input matrix. And that is because we are calculating the convolution values only at locations where the kernel is completely inside the matrix. So parts of the boundaries are removed. Next, we move the kernel one step over to the right and perform the same operation to get the next value of the output matrix. And we keep doing this until we have all the values of the output matrix. And this operation is called convolution. Now imagine you have a matrix which has depth as well. So it is a three-dimensional matrix, which is also called a tensor. We want to calculate the convolution of the kernel on this input matrix. Now you can think about this input matrix as just an RGB image. So we have R, G, and B channels, and therefore there is a depth to the matrix. It's a 3D matrix, which we will call tensor from now on. To perform the convolution, the kernel also needs to have the exact same depth. Now imagine you're moving the volume in exactly the same way you were performing the 2D convolution. But here you're moving the entire convolutional kernel cube instead of the square. And you perform the same operation, and of course the output is exactly the same dimension as before. So in this case, it is a 3 by 3 by 1 matrix because we are multiplying elements of the volume and then summing them up together, and the output dimension doesn't have any depth. To get an intuitive feel why convolution filters are useful, let's apply the convolution filter shown in the red box to this grayscale image. The green box shows a patch of the image where the filter value is being calculated. You may want to pause the video and check out the calculation for convolution operation yourself. On the right-hand side, we are showing the output of the convolution operation. In this case, because of the way the filter is designed, its value is high at vertical edges. If we change the values in the kernel, we will be able to detect other low-level features of the image. For example, we can also change the filter to create a blurring filter, a sharpening filter, or an edge filter. So to summarize, we have learned what is convolution. We have learned a 3D convolution filter used in neural networks has the same number of channels as the input. And finally, we learned a convolution filter is useful for extracting low-level features in an image. That is all we wanted to cover in this video. Thank you.